feel like this is really more of a story. You know, the middle of the talk will kind of touch on what originally was going to be the whole talk of kind of doing word vectors for Solr, but it turned out that I quickly found that I was doing the same thing there that I had done in the past with other approaches, and I was getting similar kinds of results. So I ended up trying to go in a different direction. And so now I'm going to tell a story of kind of how vectors I've used for search over the years, as well as, in particular, kind of Word2Vec and things beyond that. By the way, I'm Jake Mannix, lead data engineer at Lucidworks. We'll quickly just kind of talk about, you know, what we're going to say today. We'll do some motivations for why we would do the kind of things that I'm going to talk about with word vectors. Review a little bit of the tiny blast through where search scoring kind of started. Move on to talking about kind of the first generation of semantic relevance kinds of approaches before moving on to unsupervised vector embeddings. And then kind of at the end where I kind of diverged off from my starting point of looking at Word2Vec into doing deeper models, deeper neural models for search ranking. And it kind of ends with some stuff with triplet networks that are more speculative. And if we don't get those slides, then I guess that means it's fine because, you know, that's some more speculative stuff, and you'll see it in the slides later anyways. Okay, moving right along, who am I? It's a banana slug, by the way. I went to UC Santa Cruz. We love banana slugs. They're our mascot in the background. Ages back, I was a math and physics person, but I've been doing search, recommenders, personalization, applied ML for a long time now. These days, I'm a data engineer, so I'm building data-driven products. That's built on top of search typically. That's typically the way that works. Is that actually, see that? It's not, okay, I should keep track of that because I have to cut off stuff on the edge, tell me, because it doesn't show it like that here. Grr, that's okay. Okay, yeah, so that's me. I used to be at the Allen Institute for Artificial Intelligence, and before that, I built personalization systems at Twitter and recommenders and search at LinkedIn. And I've been at Lucidworks for about 2 years now in the office of the CTO. Okay, what do your users expect from search relevance? Search relevance, you know, these days, it's a tough problem. If you look at your query logs, no matter how good your search is, you're going to see people who are doing crazy hard searches. They're expecting misspellings to be handled seamlessly, synonyms to kind of show up, you know, search as you mean, not what you say. Acronyms should just be handled. You know, stemming should be used properly. It shouldn't always happen. It should happen when it's needed. And meaning variants need to be handled. The simple grammar query, grammar from people's queries kind of is expected to be handled by our users. People expect for the recent past queries, if you do search for, you know, a bunch of, you know, tents and hiking gear, and then you ask for, you know, burn aid, something or other, you know, you're expecting, you know, ointment for while you're camping that you got to burn or something. Like you expect that our users expect that your past searches influence your current query. The context is relevant. They also want to they want you to know that what you've liked in the past and what you've purchased or clicked on is relevant, not just for the ads that are going to follow you everywhere on the web. Sometimes even people issue different kinds of queries. They issue kind of queries that are super, super general, like I want music, and you're on like, you know, a site that has like, you know, you're selling CDs, and you have every band under the sun, and they say music. That'll be a common query. That'll actually happen. What are they doing? They're really just saying, get me to the page where I can start browsing. They don't want to use search, essentially. And they can be a little bit more specific, but still they're saying tents. They don't want the exact best tent to show up. They kind of want a list of popular tents and break it down. But sometimes you're going to get weird kinds of queries that, you know, ask for non-alcoholic treatment for dry cough. Like, you don't want alcoholic things. Like, this is a modifier, non-alcoholic for treatment, and then it happens that dry cough is the thing. It's like the kinds of searches that people want to be able to handle are fairly complex these days. Users expect this. Google has made people expect that from everybody's search engine. So how has this been handled in the past? Like all these hard things are really tricky, and people have been expecting it. So what have we been doing to to do that? We're doing really just a vector space model. And the original vector space model for IR with TF-IDF and BM25 really just kind of counts the number of times the terms that were issued match in your document, weighted possibly by how rare those words are. Super, super fast because you're basically doing sparse vector multiplication. You're not looking at all the documents. You're only looking at the ones that match. And it actually has pretty hard to beat baseline relevance. If you actually try some of the approaches, I'll talk about some of the papers that people have written in the past about kind of comparing a state-of-the-art fancy new model to BM25 out of the box. You often don't beat it, even if you're doing something super fancy with query expansion, synonyms, and all sorts of stuff. But the issues with it are that it doesn't really handle things like synonyms, doesn't handle synonymy. It doesn't handle polysemy, which is sort of the reverse of things where you have a query that, a term that actually has two different meanings. In fact, the query here is you look at the two different queries there, white tie dress shirts versus white skirts or dresses. The BM25 comparison, or the TF-IDF or the cosine similarity of those two is actually pretty high, but one is looking for kind of skirts and dresses, and the other one is looking for shirts that happen to be for a white tie event. They're not looking for ties either. So being able to kind of parse those things different in a traditional vector space model is difficult. Yeah, especially the white tie dress shirts, even Google does pretty well, but it doesn't fully dependency parse the query perfectly, because it doesn't notice that white tie is itself a modifier for dress shirt. So in fact, if you want it to be unfashionable, you can wear a black white tie dress shirt. And if you try to do a search for black white tie dress shirt, Google's not so great at being able to figure out that you want not a white shirt. You actually want a black shirt that happens to be for a white tie event, and it's of the style of a white tie dress. Complicated, hard to do. Even Google can't get that one, so feel better. So moving beyond kind of the traditional vector space model of just kind of having these sparse vector dot products, people started to say, okay, let's try to find a vector space model that doesn't show the same, doesn't consider hoodies to be completely different than sweatshirts. In particular, things like the vector for software engineer and the vector for computer programmer in the original kind of TF-IDF style on BM25 models, we'll show those two are completely orthogonal vectors. Those vectors have zero cosine, zero dot product. On the other hand, network, the query network with real estate developers and a software developer at Real Networks, if you've got stemming turned on, we'll say those are very, very similar queries, which is unfortunate. And in fact, if you think about like what the scale of dot products should be, what the scale of dot products normalized, the cosine similarity of vectors in a high dimensional space, the cosine of the first pair is 0, second pair is 0.75. Things that are totally uncorrelated should be around like 10 to the minus 3. So having 0.75 for that second pair is definitely not good. So to kind of move beyond that, there have been a bunch of different approaches over the years, and they generally fall in the realm of kind of finding a factorized model, a dimensional reduction from this 100,000 dimensional space you start in for doing the original vector space model, all the way from using the properties of the John and Lindenstrauss lemma that says you can just randomly project without even doing any smarts at all, and you'll actually preserve distances in a lower dimensional space, up through doing latent semantic indexing, which is a matrix factorization approach, or do a more probabilistic approach with latent Dirichlet allocation. I'll talk a little bit about each of those just super fast, as this was kind of the evolution of things that people have been doing to kind of approach the polysemy and synonymy problems and handle kind of the full meaning of the query. Doesn't work super well, turns out. But it does do some of this stuff. So first off, let's quick zip through like 1 or 2 slides on latent semantic indexing. Essentially it says take your term document matrix, meaning the rows are documents and the columns are terms, and you're just listing the kind of the weight of each term in each document, maybe the count of that time or maybe the full TF-IDF weight. It's a big sparse matrix, and you assume it's effectively approximately represented by a matrix product of a document by feature matrix and a features by terms matrix. And these are both dense but skinny, as my cartoon diagram will show. And I'm supposed to, it's color, so you see you have green made out of blue and yellow. That should be insane. I originally added this for doing kind of search and other kinds of things, as well as recommenders to Apache Mahout in the early days. Thankfully, it shows that a project is still moving if eventually your code gets killed and removed. So this code is no longer there. I don't think it's even there at all. It's definitely been deprecated for a while. I hope they actually removed it completely. I haven't put a lot of stuff into Mahout in a while, and I feel bad about that. But doing latent semantic indexing for Solr, you can do this. This is stuff that lots of people have done all the time, and you can do it in various different kinds of ways. You can do it at index time, where you use the decomposition to kind of add terms similar to this document that don't occur in it into a separate field, and then search over that field with a lower weight. You can also take the document vectors themselves, run clustering over all of them and index the cluster IDs, or run locality-sensitive hashing over the set, so you can quickly, not having to do a full table scan when you do your kind of dot products at runtime to actually do comparisons. Or you can actually try indexing the full vector components as fields and dot product those. But that's really, really slow. Or you can kind of store the vector there and only use it as kind of a re-ranking step. You can actually pull those out, write a learning to rank model for Solr, and use the feature of that dot product of the query's representation as LSI and the document, and use that as a re-ranking feature, the cosine similarity of those two. Or a query time. You can just do query expansion to kind of effectively get a lower weight set of terms that are similar to the query terms that didn't happen to occur in the query. Maybe terms similar to sweatshirts might be hoodie, in which case then it would expand onto that. So there's lots of things you can do here. People have done this over the years, and sometimes it works okay. But the scaling is complicated. Your dot products are now dense. You don't get to take advantage of sparsity, which is what the original vector space model has. Every document doesn't have very many of these terms in it, but every document in a LSI model has every vector component in it, with non-zero values. There's also some other issues with LSI that just comes from the fact that the way that you do decompositions, they actually tend to be it's hard to interpret the dimensions. The dimensions themselves it's not only the fact that they have negative and positive values. You don't know what it means -1 times hoodie plus 0.4 times sweatshirt. It's also that the eigenvectors that lead to this matrix decomposition have complete mixing, really, when their eigenvalues are similar. So won't go into too much of the details of that, but essentially it means that you might have an eigenvector that looks like it's for hoodies, and another one that is for iPads. And if their eigenvalue is very close to the same value, then any linear combination of those two is also an eigenvector, which means hoodies plus iPads divided by √2 is an eigenvector. And what does that eigenvector mean? Nothing. It has no meaning. And these mixings aren't due to semantic meaning. It's just due to the fact that that's what linear algebra will do. So this thing that people don't always think about when you try to interpret these columns is it's hard. And sometimes it doesn't make sense at all. But also, if you run LSI as like a raw, just compare the dot products of vectors as your ranking at all, and you'd use that instead of BM25, and you try to compare and see how well it works, it doesn't work as well. You don't get as good rankings in the academic comparisons. BM25 by itself against LSI, it's just worse, and it's slower. If you try to incorporate BM25 together with the LSI dot products, you can get a little bit better, but look at where the decimal points are better. This is maybe 1 to 4% relative improvement in precision, mean average precision on the Trek collections. This was a paper you can look up maybe 10 years ago or so, 12 years ago, maybe longer than that. Yeah, so LSI, not so super great, actually, for doing actual search relevance comparisons. It does pretty okay for kind of doing query expansions if you want to factor that in. But trying to do it for raw dot products, not so fantastic. Okay, so if that doesn't work, why don't we just try a different kind of decomposition that doesn't have some of the same problems. It doesn't have such a density problem. It is more interpretable, and so we're going to go with this thing that the Michael Jordan of machine learning, whose name is Michael Jordan, invented a while back with David Bly and a few other people. Latent Dirichlet allocation, we won't go through the real details of it, but it's like a probabilistic decomposition of the term document matrix. It's still bag of words based, but now it kind of models documents as distributions over topics, and topics are distributions over terms. One thing that people don't think about too much when it comes to LDA that's an advantage is there's a lot of sparsity there. When you run the decomposition, it doesn't look sparse, but it turns out that the weights actually do drop off very, very heavily. Each document really only has maybe log of num topics that are non-zero in a sensible way, and you can drop all the ones that are smaller, that are small. And also, the topics themselves only have log of the size of vocabulary that actually contribute in any meaningful way. These are advantages in the sense that you can actually make basically a very sparse LDA type model that every document only has a few topics in it, and that's great. You can leverage sparsity when you encode that in Solr. But it's also constraining. It also says that you're never going to get more than log num topics. If you want lots and lots of topics, you can't really get it. It scales as a vocabulary size. You can try to run more, you can try to train more, but it doesn't really work out so well necessarily. I'm not going to go through this in too much, but here's kind of a cartoon of what the LDA topics kind of look like if you run it over, say, recent news stuff. You'll see stuff where the documents, the topics themselves won't have labels like this. You'll just look at them and you'll look at them after and say, okay, that's kind of about weather, this is about current events, this is politics, this is sports. And when you run a document through it, it'll kind of label the terms. You can do that. You can have it label the terms as coming from the various topics. But in general, you're going to have that the overall document itself was maybe 50% about weather, 20% about current events and politics, and not much else. It's useful. But if you want to use it for search, which is what we're here for and talking about, you've got some pros and cons. So human interpretable topics happen. Usually, it doesn't always work, but they're usually pretty interpretable, but they're not labeled, so you have to kind of do some hand labeling. The documents themselves, they naturally cluster in the sense that sparsity gives you that. It takes a long time to train. Topics are really general. So this is the big, big scary part, is that basically you can get O of number of hundreds of topics typically. So if you want to use this for search, it's good for kind of doing topic clustering, but it's not super good for actually saying, I want my query, turn it into an LDA vector and use that as my search. Well, if it's just going to find you whether the query is about, say, the search for Hurricane Irma, it's like, well, that's a search about weather. That's great. It's kind of good for classification of the query, but if you want to use if you want to search against your index and say, now weather is my query, that's crap. That's not going to get you anything. So use it for classification and topic clustering, but don't try and use it for actual, try to beat LSI. I tried looking for papers that would say, okay, well, how do you use LDA just as a raw search in the same way people did for LDA? And I'm pretty sure it's going to be worse than BM25, so I'll find a paper that can represent that. I can't even find papers for it because no one will write it. Because they'll write a paper saying, here's all the things you could do, and by the way, of course, if we'd done this other thing, you'll find a paragraph that says, and if you tried using it for search itself, you're going to get kind of garbage. So you have to use it for what it's good for, not as a vector space model. So quick recap to kind of zip past the old stuff. If you kind of assume linearity as what your original term document matrix is, you get stuff like LSI. You can get variations on that. If you assume that kind of you started with your term document matrix coming from a solvable probabilistic distribution, you get something like LDA. There are other probabilistic graphical models, but this is the kind of things they look like. So, we've been doing lots of math. So, you know, I just felt like I have to throw up one of my favorite XKCD cartoons, in the sense that I started in the world of physics, and eventually I kind of drifted into more math stuff. But like, what we're seeing is these vector space models kind of eventually kind of drift their way down deeper and deeper into the realm of you know, various aspects of math. And once you're in math, where do they go? They go into linear algebra, and these days GPUs are what are doing them. And if you look at like going back up from the bottom of GPUs using, you know, kind of being the basis for what we do fast linear algebra with, linear algebra is doing all of what's done in deep learning these days. Deep learning is kind of taking over most of machine learning. Machine learning is taking over, you know, you can read the tweet. I don't need to read the whole thing. But this is kind of the reverse, you know, diving your way in from software is eating the world. So if we're going to move on to using kind of things that are the next thing past, you know, these old first-gen semantic models, let's try doing what my friend Reza says. Let's do a neural model. So this is like kind of the meat of where I started to make this talk, and I did work for a while on trying to do this kind of stuff. And we're going to have to see that well, this is sort of where we're going to get to. We're going to start with some shallow neural networks, and then we're going to move on to what else can be used. Just a quick super, you know, TLDR on neural nets. Really, they're still based on matrix multiplication. It's all linear stuff, and then simple element-wise nonlinearities. So they seem crazy and weird, but really it's about taking these things we did before that were super linear, or just straightforward, you know, linear operations, and just doing them again and again. And in between, we interleave a very super, you know, small amount of nonlinearity. But as has been known for a long time, neural nets are kind of, they're universal function approximators. You can approximate any nonlinear function with these things, even with just one layer. But one layer, you got to use a lot of nonlinearity. It's better to use a lot of layers with just a tiny bit of nonlinearity. Training these things is really the same way a lot of other algorithms are trained. It's, you know, often just stochastic gradient descent against a loss function. They're straightforward. It's just taking derivatives. And they can also act as generative models, so they can do this kind of stuff that LDA will do as well. So there's lots of things that they can do. So what are the most common ones that actually help? They're not deep learning models. They're shallow vector embeddings. Most popular one is Word2Vec. A similar one is Glove. Word2Vec effectively just ends up being a nonlinear factorization of the term context matrix, where contexts are some sliding window over the terms in your document. So you don't look at the whole document at a time. You look at the kind of four terms on either side of the center term, and use that as a mini document and look at that whole term context matrix, decompose that in a nonlinear way. You don't actually treat it as a matrix. You actually train a shallow neural net one layer deep. It still doesn't know anything about the rest of your document. So if you want to do indexing that actually will train vectors for your documents that aren't built up of just bag of words, you can do a little bit better than just Word2Vec, which is getting vectors for your terms, and then you can kind of average them together. Doc2Vec does a little bit better than that. It actually, while it's training, will actually get get vectors for the individual documents that kind of see some of the global structure. I guess I wanted to look at just kind of cartoon form of what these things look like when you train them. It's really just like, you know, if you're looking at the sentence, the quick brown fox jumps over the lazy dog, you start with kind of the green window around the quick brown. Should be, where does the green go to? You can go far enough over. The blue one does. But you slide your way slightly over each one. You know, if you're looking at brown fox jumps, you take the vector for fox and you kind of add on a small bit for what it already was before of the vector for the context, brown, something in between jumps, where that something in between could be any other thing that also occurs. And similarly, at the same time, you kind of inch your way toward, take the vector for brown jumps, the context, and add onto it a little bit in the direction of the vector of the fox. And you kind of inch the way, kind of, this is similar to kind of alternating least squares, where you kind of inch your way through the corpus as you slide over everything. And you do this many, many times until eventually you have vectors for all your terms, and you have vectors for all your contexts. Usually those aren't kept, because there's many more contexts that are independent than terms. But you're doing this at the same time. This is being effectively built up. So what does it get at the end of the day? What does it look like? What can you, before we can even say what you use it for, the nice thing is that Google, who kind of, some people at Google who wrote this algorithm and the paper on it and open sourced the code for it, also did something that no one ever does, where they released a model and all the data. I guess not really the data originally for it, because the data is really big. Wait, no, go back. Yes. Yeah, the data is like, they trained a model on 100 billion tokens of Google News and built a model with 3 million terms and phrases as the vocabulary, and each with a 300-dimensional vector. And just, you can download that. It's about 8 gigs uncompressed. And you can just use it without using any complicated software, because they're just vectors. You can just add them and dot product them and do whatever you want with them. If you start taking that and playing with them, you can find some really weird things where you find where are the vectors nearest to each of these terms. And these terms all occur in their corpus, and some of them have really sensible, interesting, synonyms or things nearby the vector for Lucene has Solr, Nutch. Lucene, Solr as a phrase, Apache Lucene, so forth. Some of them totally make perfect sense. All the ones for iPad are awesome. Ones for king, or kings and queens and crown princes, very cool, straightforward. Sometimes things, it doesn't really handle, for example, the polysemy problem too well. Synonyms for Java, lowercase, it's like, oh, this is about coffee. Cup of Joe. Chai latte? Okay. Joe espresso. Java capital, maybe, because I wanted to find like an example that had Java, the programming language. No, it doesn't see that. Not in Google News. Google News, it says Java's Indonesia. Or lowercase, it's about coffee. Synonyms are one thing you can do with Word Tyvek that's great, and it's a little weird, because a synonym for Obama is McCain? No, it's not a synonym. They occur in the same context in Google News. Right? This is what this model is doing. It's finding things that occur in the same places in sentences. It's the distributional hypothesis at work. But the cool thing that people have demoed a lot or showed off is that, like, oh, what's super cool with the Word Tyvek is you can do this kind of analogy, this vector analogy, where you take the vector for king and you subtract the vector for man and add on the vector for woman, and what do you get? You get the vector for queen. Well, you do, actually. You get close to it. And so I actually tried a bunch of these just a couple nights ago to get somebody to show off. But I made sure to get not just the top-ranked one, get a couple more of them, because you can deceive yourself very easily that, like, these are just all going to be magical. It's learned what language means. Well, oh man, this is not. How do I? Okay, it's only got the V's. There's a V on the other side. This is a vector of all those things. It's frustrating that it does that. But you can get king minus man, so take off the manness from a king and add on the womanness, and you get a queen. But you also get a monarch just nearby that's gender non-specific, and princess. Okay, that's a female kind of like king. But crown prince is actually male again, so not so great. But you can also do stuff like take the concept of Paris, subtract off France, and add on Germany. What do you get? Berlin. That's pretty cool. That's useful. You also get other cities in Germany that are big. You can read through these, and it's actually kind of clever what some of the stuff can do, and how it works is kind of weird and interesting. The one that I really liked that I noticed before that actually is super clever is if you take the misspelled word, T-H-E, and you subtract off the concept of the real word it should be, you're getting what does a misspelling look like, and now apply it to because. And you actually get misspellings of because, or variations of bad spellings of that. Which is like, how does that show up in just a decomposition? It's really because it's seeing the context. These things are showing up the same places, and linearity actually gets these things, which is super weird. And if you want to actually play with this live, you can come grab me over lunch. We can log into the SSH, we can SSH into my AWS box where I've got this thing kind of sitting on a running Spark shell in the background in a screen session, and we can kind of try a couple. And so I tried a weird one yesterday to try and really get something like, I want to do some really crazy, semantic analogy. I want to take, like, I want to get the notion of, I want to get the vector for the sum of country plus capital plus city. I want a country capital city, and I want to get the cosine similarity between that and, like, How do I build up that if I didn't know what a country capital city was? I'd take Paris minus France and Berlin minus Germany, Beijing minus China, get all the capitals and subtract them from their countries, and I'd get the concept of a capital. And it should be just like country capital city, except their dot product is like 0.188. Why? Why does it do that? Does anyone have any guesses? I thought it was going to, at first I thought this is going to be a great example for like where the model just screws up. It just has problems. It doesn't always work. Even if you try really hard, it doesn't always work. Turns out there's actually a reason for this. Anyone have any ideas? Any audience? Are there any amateur philosophers in the room? People, minors in college? This means this is not a pipe. This is a picture of a pipe, right? Country capital city is a description of the thing capital cities. These are exemplars of the idea of a capital city. They're not actually the same thing. One is what, and this shows up in the distribution of language, right? You don't use the word a capital city or even capital or city in the same place you would use a specific instance of a capital city. You might describe the capital city of something is this, but this doesn't show up in the same place that that capital city word shows up. So they shouldn't be the same. All these guys actually do have very similar dot products. You take the dot product of all of Paris minus France, Berlin minus Germany, they all show up in the same kinds of places. Those do have large dot products. But this is one of the weird things you can find that actually maybe is learning some things based on the way language is used that actually capture subtleties and concepts that you wouldn't have thought of. Okay, so how do we use this in Solr? I'm going to say what you shouldn't first. What you shouldn't do is all the stuff we did for LSI and LDA that didn't work, because it still won't work. It'll still be just as slow. It won't necessarily get very good dot products over the overall documents themselves. They average out stuff too much. They help a little bit, but really not much more than you would have gotten from LSI. What you should do is use it for query expansion as long as you're down weighting or not adding it as a strict OR clause, because OR will get you, oh yeah, Obama is now a search for Obama or McCain. Like people are going to get like articles on McCain that have nothing to do with Obama. That would probably piss them off. You can also use them for feature engineering. Just use that as a feature to feed into a separate model, a learning to rank model or classification clustering models. Using it to have humans in the loop to build synonym lists, you're going to get these things where you explore these kinds of things. You make a little tool that actually lets someone use your Word2Vec model trained on your data set, possibly pre-trained, use the pre-trained models from Google, fine-tune them on your data set, and then host that as a service for your internal users to actually say, okay, let's actually figure out good synonyms and ask it questions, find analogies, and you'll find lists that you wouldn't have thought of, and you can actually build those things much more quickly. But I would again reiterate, encoding them as vectors in your Solr index, you can do it. Maybe it'll do better than BM255 by itself if you mix them together. Don't rely on it as your sole scoring. It won't work. Okay, so I tried that a little bit. It didn't work so well, so I didn't give the rest of my talk on that. Maybe it's just because Word2Vec is shallow. It's a shallow neural net. We should do something deeper. We must go deeper. Should we? Is that really the right thing to do? Something to try is actually use your click data to actually train a deep neural net for search relevance. And people have been doing this for a long time, really. There hasn't been like deep neural nets. Like Bing was doing neural nets as like a key component in their search relevance as early as like 2008 or earlier. And it worked really well. They A/B tested it. They found that it got more revenue on whatever they got for more searches and stuff like that. So this has been around for a long time. But what hasn't been around for a long time are deep nets that actually understand text a little better. There are a couple different kinds that can be used on text. Convolutional neural networks and LSTMs, long short-term memory networks, both of which are able to kind of handle more of the meaning, more of the text as a whole, as opposed to the individual documents as a bag of words. What do I mean by that? You want to be able to get order in addition to context to kind of really handle your text. So to do deep learning on text for search, you want to be able to do vectors. You want to also be able to feed in vectors of your full query strings, vectors of some of the document, maybe not the whole document itself, because it's going to have many different concepts spread out over large documents, but at least document snippets, you want to be able to get vectors for those that kind of capture their overall meaning. You might also want to do the stuff we started with the talk on, handling vectors for user preferences or vectors for the recent query history. This is where deep networks are really going to shine, because Word2Vec is not going to be able to handle feeding in side channel information all over the place, whereas a neural net that's deeper and is more modular definitely will. And then you can throw them all into a big ranking model and train it on the clickstream. So I've been working on doing this, and there's a bunch of different approaches for getting deep learning for text. And you have to choose, first of all, how you're going to vectorize your inputs. You can start with bag of words, but of course then you're going to be limited by the fact that you've lost all your order. You can also do bag of words to vec, which is what I'm saying, that BOW2V, where you take the pre-trained vectors from a Word2Vec model and grab them for each of the tokens in your term and use those as your inputs. But then you're still getting a bag of those. Better to do that is do sequences. So sequences of either characters, which is weirdly, it works really well because LSTMs are able to actually remember what you saw before. So you're not looking at just one character and then forgetting what happened before. But you can also do sequences of tokens or sequences of the vector representations from a pre-trained model over time. LSTMs are really complicated, and I'm not going to go through the details of how they work, mostly because I don't know. I know some of it, but I don't know the details well enough to kind of tell you guys. But I do know that they're slow to train on really big text from what I've seen. Smaller text, they work pretty well. If you remember to let them forget stuff every once in a while, they can be trained on longer set. But they're slower than convolutional neural networks. That are effectively similar to what we talked about in Word2Vec, where you're taking sliding windows of stuff, except it's kind of, you take sliding windows of tokens, and then you take sliding windows of sliding windows, and then you can take sliding windows of those sliding windows, and you're kind of averaging them together bit by bit. And that kind of builds up. This is what people do for image, facial recognition and image analysis with neural nets. And it's kind of built for that, because there you're taking sliding patches over the actual image, and you're saying, okay, I'm building up the image out of these things that look like edges and these things that look like eyes, and I'm getting a face eventually, and it builds the features kind of from the inside out. But text is the same thing. It's just not two-dimensional already. It's one-dimensional, so you can still do that. And it looks kind of like this. You can do it for bigrams, but you can do it for bigger sets. But if you look at bigrams at a time, you look at the cat sat, and then you're making a weight for the cat, and you're making a weight for cat sat. You're going to average those together, and bit by bit, eventually you get a vector for the whole sentence that kind of came from averaging together vectors of bigrams and then pairs of bigrams, and you get a vector for that whole thing altogether. It has a limited overall size that decides how big you're making the windows, but for search, this is fine because queries aren't super long. They're short enough that this can work. So, okay, well, those are the kinds of components you can go, but what do you do? How do you train one of these things? What do you train it on? So I looked through the literature a bunch to try to find a way to train this stuff in a way that would use my clicks. Because training data for neural nets they will eat whatever you will throw at them, right? They need billions of documents if they can, if they really want to train well. And getting labeled data with billions of instances is super hard, unless you're Google or Facebook or someone like that. But we've all got click data. So click data is what we can train it on. So I wanted to find something to do it on click data. I didn't find one, but I found something that had a way of generating similarity metrics. And they did it, similarity metrics, this is a paper, the FaceNet paper out of Google, where they were finding they want to do facial recognition. And what they did is they wanted to find a distance function that says people that are the same person, but you're looking at them from different angles, should be measured as the same, but you want different people measured as far apart. And so they trained this big, many-layered CNN with a novel loss function, where their loss function was you're training on triplets of a person, someone you know, another picture of that same person that should be measured as similar, and then a person that's different. And you want to simultaneously optimize for making the similar people similar and the different person different at the same time. And I'm like, after I talked to some people at SkyMind, I was advised to read this blog post on triplet embeddings using DL4J, because DL4J is a tool I like to play with to do this stuff. And it has an implementation of that paper. But I'm not doing faces, right? I'm doing text. But that's okay. I can do it for text. You'll see. Trust me. But forget about what the neural network is. We get our triplets. Schematically, the point about these things is trying to understand the architecture of what it's trying to feed in and what it's trying to get out. I'm not going to worry about the fact that these are faces. These diagrams don't have any faces in them, right? They just have inputs of an anchor thing, a thing that's similar, a thing that's different. And then it's going to kind of join them together, feed them through a bunch of black box neural network, pull them apart, and get train a difference on train the difference between these two, make that small, train these two to get them make that big, and use that as your loss and propagate that back up through. So that's great. We can do that as long as we vectorize properly, which we talked about earlier. There's lots of approaches. I don't know the right answer for that yet. I've been working on it, but getting the right vectorization process for text that is queries and documents in the context of search in a general way is hard, so I'm specializing on some fixed cases for now. But this training process is still tricky. Like, these people didn't come out with just this interesting triplet loss method of training for getting similarity metrics. They also used this technique of curriculum learning effectively, where to get the network to converge very quickly, they would start by saying, let's get a variation on the same face. Maybe it's just got noise applied. It's just in a slightly different lighting setting, or maybe even applied artificial noise. Those are the two that are similar. And then a totally random other person is the dissimilar one. And you start training to learn, easy stuff first. Get kind of fast. Let the learning rate be fast to start with as you do that. And then as you get on further, you want to start picking harder and harder cases to distinguish. Something that are obviously the same person, but from a completely different angle, and maybe it's got different colors and different lighting and different sizing. And then the other person is someone who your earlier iterations thought were the same, and they were wrong. And so feed those back in as now negative examples to again train. And kind of do this whole curriculum where you speed up the process that way. So how would you do that for search? Nice thing is for search, if you've got a lot of logs and you do some proper rank debiasing on your click-through rates, you actually have like a kind of training set that already has curriculum learning kind of built in, ready for it. In the sense that you have stuff that showed up at the top and got clicked on really well, and that's really good, similar, easy results. This is the easy stuff. And then you've got stuff that showed up further down the page that wasn't clicked on. That's how you start off as negative samples. Or maybe pick random documents that didn't even show up in the result set as dissimilar to start with. But then you start getting to the point where they had larger and larger, closer and closer to the boundary. You've got an actual decision boundary in your click-through rate logs, right? That actually say this document appeared at the top rank according to a search engine and got slightly less than what we would have expected click-through rate there. So basically done. We're basically out of time. And the big question would be, Magic 8 Ball, does it work? Does using this deep net for search ranking work? Well, signs from the prior on selection bias for who would present stuff would point to yes, right? That would be your baseline assumption. If you were at an academic conference, I would not be presenting if I didn't have, yes, and here's my metric that shows it beats the state of the art by X%. Haha, yes, I get to get tenure or get another grant or whatever it is. But actually, it's reply hazy. Try again later. We don't know yet. It takes a long time to train these models, and I'm not getting. You want to do cross-validation on these things to do hyperparameter training. It takes a long time. Playing with GPUs on AWS is fun, but costs a lot too. So you don't want to use a giant fleet of them unless you got tons of money. And this is a research project, so we don't know for sure yet. But if you want updates on it over time, email me or follow me on Twitter, and I maybe will blab about it. But you can also invite me to come talk at your conference or meetup or whatever. Give me a couple months probably, because it probably won't be done anytime soon. But we'll see. I have hopes that it will get somewhere. But this is tricky stuff. Thank you.